Okay, so we've talked about these measures of center, spread, and position or dispersion. Um, Time to take a little bit of a look at what do they mean? What are they used for? Why do we care? Well, the big ones that have meaning to us are the mean and the median, of course, and the standard deviation. And again, it comes back to this bell curve. Come on. Try to draw a decent bell curve here. Close enough. If it's tipped a little bit, but that's okay. Just tilt your head just a little bit to the right. Looks good. The right, Cody. There you go. Anyway, so if the data is well distributed, normally distributed, of course we talked about the measure of center, the mean or the median will be at the center. We tend to use the mean for this. Like I said, it shouldn't matter. The mean and the median should be in the same location. And exactly half of the data should be below the mean and half the data above the mean. So you're looking at 50% here, 50% over here. But we can break it down even further than that. This is where the standard deviation comes in. If we go a standard deviation below the mean, I'm going to write it as -1 standard deviation. So 1 standard deviation below the mean. Between the mean and that 1 standard deviation below, normally in most statistics courses I teach, I say approximately 34%. Your textbook uses what's called the exact or detailed version of this. So they're saying 34.13% of the data is between those two values. And if I were to go the other direction, 1 standard deviation above the mean plus 1 standard deviation, the same percentage is between the mean and that value, 34.13%. So what this is telling us is over 68% of our data should be within 1 standard deviation of our mean. What does that mean? What does that tell us? Well, let's say that, for example, we have a set of data that has a mean of, of 42 and a standard deviation of 9. What that's telling us, if you look at the curve, the mean here would be 42. This would be 1 standard deviation below, so 42 minus 9 would be 33. 1 standard deviation above would be 42 plus 9, or 51. It is telling us that over 68% of the data should be between 33 and 51. If it's more than that, well, that means it's tighter than a normally distributed set of data. If it's close to 68%, it's approximately normally distributed, is what that's telling us. So let's keep going. If I go another standard deviation out, so this is -2 standard deviations now. Between the 1 and the 2 standard deviations, we expect about 13.59% of the data to fall. And the same on the other side, if I went out to +2 standard deviations. I expect about 13.59%. So if I were to add all of those up, it's actually almost 95 point, it's a little over 95.4% of the data would be within 2 standard deviations of the mean, over 95%. If I go off of this here, if my standard deviation was 9, I subtract another 9, 33 minus 9 would be 24, 51 plus 9 would be 60. I'm expecting 95% of my data to be between 24 and 60. Again, maybe a little less, maybe a little more, but close to 95%. If I go down another standard deviation, -3 standard deviations, I expect about 2.15% to be between 2 and 3 standard deviations away on either side. So again, the values that would correspond with this set of data, if the standard deviation is 9, going down another 9, this would be at 15. Going up another 9, this would be at 69. And then smaller than that, smaller than 3 standard deviations below the mean, only about 0.13%. Or larger than 3 standard deviations above the mean, only about 0.13%. So that's saying is very few values are more than 3 standard deviations away from the mean. These percents in here never change. They're the same. It's these numbers down here that change. The means, then the standard deviation, change those numbers. So let's take a look at another example. You could, but there wouldn't be much out there. So I'm going to put these percents in here because those don't change. 34.13% on both sides. 13.59% on each side. 2.15% on each side. And 0.13% on each side. Notice I didn't put any numbers down on bottom yet because I don't know what they are yet. But the percents don't change. Let's say that you decide you're going to move and you want to buy a 3-bedroom, 2-bathroom house. And you look at the area that you're looking to buy in. The mean cost of a 3-bedroom, 2-bathroom house is $138,000. With a standard deviation of about $32,000. So what's that telling us? That's telling us that the center of this curve is 138,000. I'm going to leave the zeros off and just put 138 there. What would be this number right here, one standard deviation below? It'll be 138 minus 32,000. This will be 106,000. What's this one going to be? Well, subtracting another standard deviation, subtracting another 32,000. This is going to be 74,000. This one's going to be subtracting another 32,000. It's going to bring us down to 42,000. Everybody see where those 4 numbers just came from? Any questions? Going the other direction now, what's this one going to be? Well, 138 plus a standard deviation of 32 is 170. This is going to be 202,000 and 234,000. Now let's say you find a house that is 3-bedroom and 2-bath that you just fall in love with. It's just absolutely perfect. It has everything you want, laid out the way you want it. The price is let's do this. The price is $202,000. I'll leave it right on the line to make it easier for us. Your real estate agent tells you you need to put in an offer on this house right now because it's going to go quick. What all this information is telling us, if we find $202,000 on this curve here, it's right here. What that is telling you is, if I add these percents together, is that only 2.15 plus 0.13 is 2.28%. Only 2.28% of all 3-bedroom, 2-bathroom homes would cost more than $202,000. Or if I went the other way, if I were to add up these percents, 97.72% of all of those 3-bedroom, 2-bathroom homes are cheaper than $202,000. What that's telling us is 97.72%, there's a pretty good chance you're going to find another one that you like that's cheaper. Make sense? Let's say you want to look at your production. You get a new job. And on your job, you think you're doing a pretty good job. So what you find is that your hourly production is 62 units per hour. And for the whole establishment, the mean hourly production is 56 units per hour with a standard deviation of 6 units per hour. I'm going to crunch down my curve just a little bit here. It's a little uneven that time. Again, these percents do not change. I'm just going to label one side here because the percents on the other side are exactly the same. What's going to go in the center of this curve? The mean is 56. What's going to go here? I subtract the standard deviation. I subtract 6. So this would be 50, then 44, and 38. What's going to go here? 62, and 68, and finally 74. I probably should put the rest of these percents in since we're going to be on this end of the curve. You are at 62 units per hour, which is right here. If you add up these percentages, that means you are doing better than 84.13% of employees. That's pretty good. On the other side of that, let's say that you get out of college, you get your degree, and you're offered your first job. And your first job offers you pay of $17.20 per hour. Sounds like pretty good money, but it requires you to move to a different area. So you look at that area, and you look at just the field that you're going into. In that area, in the field that you are entering, the mean pay is, oops, be careful I do this, is $21.40 per hour. The standard deviation is $2.10 per hour. So in the center of our curve is going to be, now a lot of people are tempted to put the 1720. Why does that not go in the center? It's not the mean. That's the single value that we're looking at. The mean has to go in the center. So 2140. Next is going to be 2140 minus 210, or 1930. Minus another 210 is 1720. Minus another 210 is 1510. We don't need to go the other way. We could if we wanted to, but your pay is right here, 1710. So put 2.15% in there and 0.13% here. What that's telling you is that only 2.28% of employees in that field are making less than what you've been offered. So it's probably not that great of a paycheck. So let's say you go back to them and you tell them, hey, that's not enough. And they come back and say, okay, we'll offer you $19.30 per hour. Well, let's fill in a number here. This would be 13.59. So now if you add up those percentages, what you're getting is 15.87%. You're making more than 15.87% of the field. So the question is, that looks like it's pretty bad. But you got to remember, you're just starting out. So it might be more telling. This is one of the problems in statistics is you have to compare, you've probably heard the term, compare apples to apples. You can't compare your starting pay to everybody who's currently working in the field. You have to compare your starting pay to people that have just started in the field. What is their starting pay, or what was their starting pay when they started? And compare that.
In 5 years, you don't know how much you're making.
Well, that's just it. It could be a field where after a probationary period, your pay increases greatly. Who knows? But that is one of the things that curve is used for, is you can actually find approximate percentages, or if you wanted to use the term probabilities, you can find probabilities off of that curve. What is for the first example we did with the house, how likely is it that you're going to find a house that fits your needs that's cheaper? Well, 97.72% of homes in that area that are 3-bedroom, 2-bath are cheaper than the one you just looked at. You can, but notice that there's only like 0.13% that's below that price. So it's saying you're probably going to find one that's in pretty rough shape, and there's not many of them out there. I mean, that's not saying you can't find one that's $6,000. You might. There's just not a lot of them there. Just like there might be on the other end, you might find one that's $2 million. There's just not many of them out there. There's another tool that gets used called a Z-score. Now what we'd used up above is called the empirical rule. And it just, like we saw, it just breaks that bell curve down into percent so that we can find approximate likelihoods or percentages, probabilities from that curve. But you'll notice it was only useful if the numbers we had were right on a standard deviation step away from the mean. Z-scores are a little bit more flexible. They don't give us a percentage, but they do allow us to compare two things that are seemingly unrelated. Z-scores are actually part of what you call norm-referenced tests, if you've ever heard of that. Norm-referenced. We're taking two things that are from different populations, as we discussed last week, the samples and populations and all that, and you're able to compare them to each other. Let's take a look here at just what a Z-score is. What a Z-score does is it takes a given value and it subtracts the mean, or what's presumed to be the mean of that population from it. Then it divides that difference by the standard deviation for that mean. So let's go back to looking at the houses, where the mean price of those houses was $138,000. The standard deviation was, what was it, $32,000? And let's say you find a house that has a price of $154,000. The Z-score for that price is going to be that value, and again, I'm going to leave the zeros off. 154 minus the mean of 138 divided by the standard deviation of 32. 154 minus 138 is 16. Divided by 32 is 0.5. Now it's important that we note that that is a positive 0.5. A Z-score that is positive means that it is larger than the mean. 0.5 means it's half a standard deviation above the mean. If we were looking at that curve, here's the mean at the center, here's one standard deviation. We're right here, right in between the mean and one standard deviation above. Obviously, since it's a positive z-score, we're above the mean. There's still more than half of the prices that are below that. But being only half a standard deviation above the mean might not be a bad deal. Let's say you want to maintain your standard of living. So you look at your current house. Your current house has a value of $114,000. So does that mean that that $154,000 house is a step up, a huge step up? Well, we can't tell because you currently live here and you're looking at homes that are in another location. So let's say that where you currently live, the mean cost of a 3-bedroom, 2-bath home is $102,000. With a standard deviation of $24,000. To find the z-score for your home in this location, yours is 114. Again, I'm going to leave the zeros off. Just 114 minus what? Subtract the mean, which is 102, and divide by the standard deviation, which is 24. 114 minus 102 is 12. Divided by 24 is 0.5. So your current home is 0.5, or half a standard deviation above the mean in your current location. So that house that priced at $154,000 would be in about the same quality level of your current home, about a half a standard deviation above the mean. Well, let's look at another way of using this z-score. All of you took some sort of entrance test to get into the school. You had to take a math and a communications test. So we're going to, just to make it easier, we're going to talk about English and math tests. And let's say that on your English test you scored a 38, and on your math test you scored a 29. Does that mean you did better on the English test? Not necessarily, no. The math test may have been a lot harder. The way you tell is you use the z-scores. Let's say that all people that took the English test, the mean score was 32. And the standard deviation was 6. For the math test, let's say the mean score was 24. And the standard deviation was 4. Now you might look at this and say, hey, we were 6 points above the mean for the English test, only 5 points above the mean for the math test. We did better on the English test. No, not necessarily. Let's get to the z-score. The z-score for the English test. How would we find it? Our score of 38 minus the mean score, which is 32. Then once we get that difference, we divide by 6. What's 38 minus 32? 6. 6 divided by 6 is 1. You're 1 standard deviation above the mean. In your notes, I want you to find the z-score for the math. So we have 29, which is our score, minus the mean of 24 divided by 4. 29 minus 24 is 5. Divided by 4 is 1.25. It's positive, which means it's above the mean. That's saying you were 1.25 standard deviations above the mean on the math test. You did better on the math test.
Just
Slightly better, but still better. Another way of looking at it, and that's how they do norm reference tests, by the way, to compare them. They're not just taking your score and comparing it to other scores. They're comparing it to the mean and the standard deviation of everybody who took that test. Let's say that you, in high school, they do the testings every year. And let's say that 1 year, and we're going to ignore the percentiles for now, we're just going to look at your raw scores. Let's say that as a junior, you take the test and you score a 68. As a senior, you take the same test and you score a 59. Does that mean you scored worse as a senior? That's just it. They randomly select the version of the test, or they make new questions every year. That second year, the test may have had more difficult questions on it. May have been a more difficult test. So again, they compare you back to the whole group of people who took the test. Let's say this first year, the mean score was 74 with a standard deviation of 16. Let's say the second year, the mean score was 68 with a standard deviation of 20. So your Z-score for the first year, how do we find it? 68 minus 74 is over 16. What's 68 minus 74? So negative 6. Negative 6 over 16 is 0.375. What's that mean? It's actually a negative 0.375, by the way. Yes. You did slightly worse than average. You were 0.375 standard deviations below the mean. Second year, let's find your Z-score. How do you find it? Okay, 59 minus 68, your score minus the mean, over 20. 59 minus 68 is negative 9. Over 20, negative 0.45. You did do worse the second year, but not as drastic as it goes from 68 to 59. Looks like you did horribly worse. You just did slightly worse. Or, of course, it could mean that you just were with a smarter group of people and everybody else did better, too. It's hard to say. Okay, well, testing isn't a real practical application. Let's look at a more practical application of this. Let's say that you are a manager of a large retail department store, and you've been told that you need to let go of at least one of your salespeople. And you have it narrowed down to 2 people. You have Pat and Jim. Okay, we'll go with that. Pat and Jim. What you have decided is that whoever has the lowest sales next week is the one who's out the door. The problem is Pat works in toys. Jim works in electronics. Would it be fair to just take the raw sales and whoever has the lowest dollar amount, get rid of them?
Well, not really, because if it's some sort of season, people might buy.
Well, if it's Christmas season, there might be toys flying off the shelf like crazy.
Or
electronics. Or most of the year, the electronics probably sell more, mainly because they're more expensive. So let's say that during this week, Pat has $2,400 in sales, and Jim has $3,700 in sales. Of course, in order to compare them, we need to use the Z-scores. We need to standardize them so that we can compare them fairly. Let's say that for the toy department, all salespeople in the toy department, there was a mean sales of $3,500 with a standard deviation of $400. For electronics, all the salespeople in electronics, there's a mean sales of let's go 6,700. No, 5,700, I should say. Yeah. With a standard deviation of $800. In your notes, quick, determine for me which one did the worst job. Okay, so Z-scores. For Pat, what'd you get for Z-score? Everybody wants to be brave? Negative 2.75. Perfect. It's 2,400 minus 3,500 over 400. This is a negative 1,100 over 400 is a negative 2.75. For Jim, what'd you get for the Z-score? Negative 2.5. Perfect. 3,700 minus 5,700 over 800. It's a negative 2,000 over 800 is a negative 2.5. Who did worst? Yeah, it was Pat. Pat's out. It was good knowing him. So these are tools that are used if you have different sets of data that have different just different parameters, different means, different standard deviations. You can still compare them by using the Z-scores. Yeah, as we showed, you can compare home prices from one area to the next by looking at the Z-scores. In the example we saw, your home was half a standard deviation above the mean for the area you lived in. The home we were looking at was a half a standard deviation above the mean. So approximately on equal ground. So anyway, let's take a look then at the next step is probability. Your textbook doesn't get into probability very much, so we're not going to talk a lot about it. There's just a few little things we want to bring up. So one of those is just our basic probability, counting. The center of probability is simply counting. The probability that something will occur probability of an event is the technical term for it, is equal to, now the results of an event are outcomes, what we call. The number of successful outcomes or results divided by the total number of outcomes. So let's simplify this. Let's put this in a simple example. You roll a die. What is the probability that you're going to roll a 2? That notation is probability of having the result be a 2. Well, a normal, standard, fair, six-sided die. No, not a fancy one. Now, first of all, we're making an assumption that all these results are what we call equally likely. So as long as it is a fair die, they're pretty much equally likely. There's actually been a lot of studies done that have shown that on a fair die, they're not completely equally likely. They're slightly more likely to come up 6. But anyway, yep. It's just the weighting of the die is slightly off.
When you drill out the notches, it's slightly going to be heavier on the one side than the
Yep,
material.
exactly. And I mean, you have to roll the die. It's a machine rolling the die to make sure it's fair, and they have to roll the die like 2,000 or 3,000 times to get a significant difference in results. So I mean, it's not a big difference. But anyway, the probability of rolling a 2 on a die. How many outcomes are there? How many possible results are there on a fair six-sided die? 6, 1 through 6. How many of those would give you a 2? 1. So there's 1/6 is the probability of rolling a 2, or a 0.16667. Technically 0.1666666, but we got to round it off somewhere, right? What's the probability of rolling an odd number? Well, how many results are on the die? Still 6, right? How many of those would be odd numbers? 3 of them. 1, 3, and 5. There's 3 of them. So that's 1/2 or 0.5 probability. Technically, you're slightly more favored to get an even number. The numbers on the die are paired up. 6 is across from a 1, 5 is across from the 2, 4 is across from the 3. Slightly more likely to come up 6 than it is a 1, slightly more likely to come up a 4 than it is a 3, and slightly more likely to come up a 5 than it is a 2. Notice, though, that 2 out of those 3 are even numbers. It's slightly more likely to come up even than it is odd. But again, theoretically speaking, they're not going to. And we're talking like very, very tiny differences. So we're just going to assume that they're all 1/6 and not worry about it. It's 1/2 and 1/2 for even or odd. So anyway, let's look at flipping a coin. What is the probability of flipping a coin and getting heads? Well, how many possible results are there on a coin? 2. How many of them are heads? 1. Now again, there have been a lot of studies done that have shown that it's actually slightly more, with pennies at least, it's slightly more likely to get heads than tails. If you flip it 1,000 times, you're coming up like 520 heads and 480 tails. But again, we're assuming that it's equally likely to get heads as it is tails. Another example. Let's look at marbles in a box. Let's say we have 20 marbles in a box. Of those marbles, let's say that 8 are red and 12 are blue. What is the probability that we'll reach into that box and pull out a red marble? There's 20 marbles in the box and 8 of them are red. So that'd be 0.4. Or if you want to reduce that down to, what, 2 out of 5? What's the probability? It's kind of ironic to put the red and blue. Of reaching in and pulling out a blue marble. There's 12 blue out of 20, or 0.6. So it is quite a bit more likely to get a blue than it is a red. Let's say I reach in there and I'm going to pull out 2 marbles. What is the probability I pull out a red marble and another red marble? Well, right now, we don't have enough information. Technical terms are replacement or with replacement or without replacement. What does that mean? Well, that means is if you're going to do more than one thing, do you reset the whole thing in between? If I draw out one marble and I'm going to draw out a second one, before I draw out the second marble, do I put the first one back in? Do I replace the first marble? And in order to do 2 marbles like this, we have to know. Let's say we're going to do it with replacement. That means after we draw the first marble, we put it back before we draw the second marble. So this is telling us the probability of the first marble being red is 8 out of 20, or 0.4. Now before we draw the second marble, we put that one back. Now if the first marble was blue, we're done. We don't care what the second marble is. So we're assuming that the first marble is red. We put it back and we draw out a second marble. What's the probability that second marble is going to be red? Well, 8 out of 20, or 0.4 again. The probability of both of those occurring, of getting the first one red and the second one red, is found by multiplying 2 probabilities together. So if there's a probability of 2 probabilities that have to both occur, the probability of both of them occurring is found by multiplying them together. 0.4 times 0.4 is 0.16. So the probability of both marbles being red is 0.16.
Not too good.
Not that great. What's the probability that both marbles are going to be blue?
That's slightly higher.
Well, yeah, there's more blue, so it should be higher. Let's take a look. What's the probability of the first marble being blue? Yes, with replacement still. Well, it's 12 out of 20, or 0.6. We put it back before we draw the second marble, so its probability will be what?
The same.
12 out of 20, or 0.6. Again, the probability of both of those events happening is found by multiplying them together. That's 0.36. So that is considerably larger than 0.16.
What's the chance that you'll fall out through end of it?
But we'll get to that. Let's go back and do this without replacement, though. So what's the probability of pulling out the first one red is still 8 out of 20. But now we don't put it back. Now remember, if the first one was blue, we don't care. So we're assuming that if we're drawing the second marble, the first one was red. So now how many red marbles are left? 7 out of 19. So now we're looking at 8 times 7 is 56. 20 times 19 is 380. 56 divided by 380 is 0.147. If we don't replace the first marble, the probability of getting both of them red is considerably lower because there's one red marble missing after the first draw. For the blue, well, the first one's still 12 out of 20. And again, if that first one is red, we don't care about the second one. So if we're drawing a second marble, we assume the first one was blue. How many blue marbles are left? 11 out of 19. So 12 times 11 is 132 out of 380. So this is going to be 0.347. So you can see, again, significantly lower than if we put the first marble back. So you asked, what's the probability of pulling out one of each? The question is, does it matter whether the first one is red and the second one's blue, or the first one's blue and the second one's red? I think it would matter. It does matter. So let's say what's the probability of pulling out a red followed by a blue with replacement? What's the probability of the first one being red? 8 out of 20 or 0.4. Put it back. What's the probability of the second one being blue? 12 out of 20 or 0.6. Multiply those together is 0.24. Now, if it's being replaced, what if I did it the other way around? Probability of blue and then red. What's the probability of the first one being blue? 12 out of 20 or 0.6. Second one being red? 8 out of 20 or 0.4. Still 0.24. Doesn't matter. No. The only way it would matter is if, well, if you weren't replacing, it's still going to be the same probability. If you're not replacing, this is going to be 8 out of 20 and then 12 out of 19, which is 96 over 380. This would be 12 out of 20, 12 out of 20, and 8 out of 19, still 96 out of 380. Make sense? What does matter is, if you were to just say what's the probability of getting one red and one blue, you'd have to account for the fact that it could be done in either order. And it gets a lot more complicated, and we're not going to get into that. let's say I'm going to flip 2 coins. Let's say I'll start with 2 coins. I'm going to flip 2 coins. What is the probability that both are going to come up heads? Now, what's probably the first one's going to come up heads? 0.5. Now, is there anything to replace here?
No.
No. You don't run out of heads on a coin, right? What's probably the second one's going to be heads? 0.5. So probably that both of them are going to be heads is 0.25. So the probability of getting 2 heads in a row is 0.25. What if I've had 7 heads in a row? What is the probability that the next one, next one is heads? Does it matter that there's been 7 heads in a row? No. It's still 1 out of 2 or 0.5. A lot of people, it's going to be heads or it's going to be tails. It's going to be one of the two. It doesn't matter what the previous flip was. The coin does not have a memory.
What's the chances of getting 7 heads in a row?
Very good question. What is the chances of getting 7 heads in a row? Well, 0.5 times 0.5 times 0.5 times 0.5 times 0.5. How many is that? 5? 0.5 and 0.5. Exactly. In math, when we multiply the same number several times, we just do powers. 0.5 to the 7th power is 0.0078, which is less than 1%. That's 0.78%. Less than 1% chance of getting 7 heads in a row. Although, let's say you're going to flip a coin 100 times. Chances are that within that 100 flips, there will be at least one run of 6 or more that are the same, either heads or tails.
The chance of getting all 100 heads is just basically none.
At one time, I don't do as many statistics and probability stuff as I used to. At one time, I used to teach a classroom section of statistics for another institution down in Chippewa Falls. And what I'd do is I'd send the group out. I'd divide the class into 2 groups. And one group was supposed to take a penny and flip the penny 500 times and write down the results. The other group was just supposed to make up the results. Just go head, tails, head. And if you look at the list, it's actually very easy to tell which one was made up and which one was actually flipping the coin. Because the list that was made up, usually they won't have more than like 3 heads or 3 tails in a row. And with 500 flips, there should be at least a run of 8 in a row of the same at some point in there. But we're not going to get into that. It is about time for our second break, so let's go ahead and do that. We'll come back at 7:27 to finish off the